All right. Yeah, then very happy to be here and walk you through the second half of this lecture. We have already heard some introduction into the field of embodied AI. Now we get a bit more practical, focusing on the topic of reinforcement learning, what has just been introduced, I would say on a rather theoretical level. So in the second half of this lecture, we'll be kind of looking at robotic applications of reinforcement learning in particular for dynamic robot control. So let's get started. When we look at industry these days, then we see like robotics in these kind of applications. So we see the robots on the left, they are there for decades. We see also in logistics applications, robots on the right. These are there for, let's say, 1 decade right now. And these robots, they have in common that they have limited kind of intelligence. They walk on predefined paths. They follow predefined motions. And this is changing right now. And it's changing because of embodied artificial intelligence. And here are like a couple of examples what these new robotic systems tend to look like. So we are talking about robots that move dynamically, packets, for instance, as here in this case from Boston Dynamics. From a recent startup from ETH, River, we see some mobile manipulation where robots are actually delivering packages to the houses. Or, of course, I mean, we're in 2025, so we, of course, also need to talk about humanoids, which are also one big application area of artificial intelligence. And why are we talking about reinforcement learning? We are talking about reinforcement learning because we can't solve everything with classical algorithms these days. And this has a couple of reasons. So on the one hand, we just can't model the world in all detail. This is just a fact that we need to live with. And also, we want our robots to be more and more flexible. This means that following predefined programs is somewhat limiting when it comes to new tasks. So learning new tasks, adapting to new tasks becomes also one kind of criteria where we evaluate robots here. And of course, also we want to set up these robots as easy as possible to adapt to new environments, for instance. And all these things is what kind of gives the new promise to the application of reinforcement learning for robotics control. So we are talking about automating the learning process somehow. So Professor Behnke already talked about that we don't describe how the problem is solved, but we describe what the actual problem is and what we want to achieve with these reward signals. So this is a totally different approach than what we would have done in the early days. And we have also some things where robots need to adapt to new environments, new tasks. So we are talking about adaptability and continual learning. So one thing where reinforcement learning matches transfer learning, also continual learning. And of course, we just can't only not model the world precisely, but we also somehow have malfunctions in the robots, in the environments where they move in. And this is where ideally these control policies, these learn control policies also should be robust against. And these are all things where reinforcement learning comes into play. And I would like to take maybe 5 minutes to walk you through the last 10 years of achievements in reinforcement learning, because this is basically where it became really interesting for us as a robotics community. So this is 2015. Until then, reinforcement learning mostly has been theoretical, I would say. And this is where it started to slowly become interesting for the robotics community, because we went away from these Atari games that we see on the left, where we would typically be limited to discrete action signals, as Professor Behnke just said, and we moved to something that became a bit more continuous in the sense of these simple simulated robotic systems that we see on the right. So for instance, something like a double inverted pendulum that you may know from control theory classes. So these were things where the RL algorithms actually have been adopted for to also work on these continual domains. And of course, as the real world and also where the robots live in they don't take discrete actions. They don't decide between a 1 and a 10, like on a grid or the tic-tac-toe example that we have seen, but they need to work in the real world. So this is why we are talking about high-dimensional observations and continual actions, basically. And this happened in 2015. Moving to 2017, you see we slowly start to move into the robotics domain. So we see first examples from the manipulation side, and Professor Behnke already mentioned that the reward in the second we take it may be not the most important one, but maybe it's more like a long-term thing. If you imagine you have this robot and the goal is, and the reward is formulated to move this block to a certain location, then this is not happening in a couple of milliseconds, but it's a process that takes maybe a couple of seconds. And this is where some algorithmic contributions have been made so that we can tackle these sparse rewards that are more like in the future. This, of course, is important for each robotic task that we look at. And on the other side, people also started to think about, hey, what happens if we move from the simulated world that we have seen until now to the actual physical robot? So this is called a simulation to reality, or sim to real transfer. And the first method that has been developed is called domain randomization. And this is what you see on the right. So instead of having one simulation that looks exactly the same all the time during training, you have a lot of variations that you see there with these different colors and shapes and so on. And you kind of randomize how the simulation looks like. And the idea is of this method that the real world then somehow is falling under this distribution of randomized environments, so that the physical robot and the policy that is trained for this robot in these simulations works as well in the real world as it does in simulation, which is, of course, the goal that we have when training these agents. Okay, jumping to 2019, so things start to become more interesting. Also from the, say, worldwide attention, it gained more. So the Rubik's Cube example from OpenAI is probably one of the most famous and first breakthroughs in reinforcement learning for robotics. So the goal is actually of this robotic hand to solve the Rubik's Cube as we know it. So it's a long problem. It takes even good humans, it takes a couple of seconds, and otherwise a couple of minutes. So this is like a long horizon task that has been solved. And another kind of milestone that was achieved in the field of locomotion. So we see a quadruped robot on the right, and with some new methods in how to model these robots, how to bridge the sim-to-real gap. There was actually the first big application on these quadruped robots that are trained solely with reinforcement learning for dynamic motor control. And let's jump 3 years further. So the examples that we have seen so far, they have one thing in common. They needed huge amounts of compute to train these things. So this means OpenAI, they spent like thousands of hours of training the control policy on a cluster, and this costs, of course, money. So only available kind of solving these AI models was only available to a very small subset of persons in the world. And this changed in 2021 and 2022 with the first simulators that you could run on your notebooks. So, for instance, the Isaac Gym simulator was released in 2021, and this was kind of the first GPU-accelerated training framework that just works on the graphic cards that you could have in your notebook. And we see here one application of this from ETH Zurich from 2022, where they use this kind of simulator, just one graphics card, to train locomotion policies of the animal robot that we see on the right in just 20 minutes, which is, in comparison to what we've seen for the Rubik's Cube, orders of magnitude faster and cheaper. So this was kind of the turning point where reinforcement learning for robotics applications became like available to the whole research community of the world, because you just can do it basically on your notebook within a couple of minutes. And yeah, this is where I stop with the historic overview, because from here on, of the last 4 years, we could fill a whole lecture with easily. So just to give you some examples of what has been achieved from the community so far. So right now we see reinforcement learning agents that control robots of any kind. So we have robots, quadruped robots, walking across like very rough terrains. We have robots running at fascinating high speeds. We have robots on the right that we see that perform like also locomotion and manipulation simultaneously. So this whole thing of mobile manipulation trained end to end with reinforcement learning. We see balancing robots. We see humanoids robots, which are being trained from scratch, end to end sensory observation, to motor outputs. Or also one of my favorite examples is like champion level drone racing from Switzerland again. So they have recently achieved beating the world best kind of drone pilots with drones steered by reinforcement learning trained policy. So let's wrap it up here for this and just see that we have lots of things going on in reinforcement learning right now, making it the de facto new control paradigm for dynamic robots. And kind of in the remainder of this lecture, I would like to highlight and just give a glimpse of 3 different aspects of reinforcement learning for dynamic robot control. First, talking about how we can make it more efficient and kind of have our robots perform better in the end. Then we look at a specific application, like a case study, where it's probably very easy to follow and bridge the gap from the theory to the application. And lastly, I would also like to mention a few things about the choice of action space, which can make a very big difference when training these robots. So let's look at the kind of how we can make reinforcement learning more accessible, how we can make it more effective, more efficient when training the robots. And we have already heard in the introduction about the paradigm under which very much of the research that we do at Lamar evolves under. And as you see, of course, with reinforcement learning, we come from the data-driven side. So if we're training in simulation, we generate lots of synthetic data. But the question is, how can we integrate additional knowledge and provide context to these models to train faster? Generally, so one part of the Lamar research is focusing on this, in particular for the field of machine learning. And now we want to look at how this maps to reinforcement learning in detail. And the basic ideas, and if you walk through like this training pipeline of reinforcement learning, you typically would start with describing mathematically the problem formulation. You decide about different learning strategies that you can go with. You can also add a particular structure to the task, as we've just already heard. And of course, you want to also think about and consider the symmetry factors to actually transfer these trained policies to the real robot. And at each of these dimensions, you can basically add knowledge at certain levels. And this is what I want to kind of provide a bit of guidance how this can work. And these 2 dimensions that we are typically interested in are, on the one hand, the efficiency. So how fast we can train our robots, how much resources do we need? And on the other hand, of course, we want the robots to perform the tasks as good as possible, whatever good means for your particular task. And this is where we are talking about guided reinforcement learning or knowledge-guided reinforcement learning that comes into play to achieve both of these things at the same time. We can skip a couple of definitions here and jump to the taxonomy, which kind of provides a good first estimate of what kind of knowledge sources we actually have and which tricks we can push into reinforcement learning to make it more efficient, make it more effective. And this is what I will briefly walk through. So some of these may be familiar, but we can see that we have different kinds of knowledge available, of course. So we have scientific knowledge, so everything that can be formulated as equations, this can be integrated. We have, so to say, world knowledge, so everything that we humans intuitively know from interacting with the world, but the robots don't know it when they are trained from scratch. So this is something we can provide them with. And of course, we also have some expert knowledge that may be available to people who are very in detail in the work with their robots, but the robots also need to be aware of this. And these are three dimensions where reinforcement learning can benefit from. Walking step by step through it. So when we're talking about problem representation, this is what Professor Benke already mentioned in the first part. We first want to define what the policy sees. So what the observations of the policy are. And there are many degrees of freedom to select which sensory inputs and which format makes sense. Second part, of course, we want to be very aware of how we formulate mathematically the task that the robot wants to learn, because this can make a whole difference between learning the right thing or the other way around. And the last thing is we want to make sure that the robot can do what it needs to do in order to achieve this task. So this is called the action space, and one thing that we also look in the last part today. There are different ways of formulating learning strategies. So don't want to walk too much into the details here, but we have already heard learning from human demonstration can be one thing. Parallel learning means basically what we have just seen in the locomotion video, so that we don't train just the robot policies on one robot, but in simulation we can train on thousands in parallel, which is kind of a pretty good advantage of this digital reality. We can, for instance, when we have a very difficult task to solve or to learn, we can start with doing it in a stepwise manner. So we can start with simplified tasks. And as the robot learns these simple tasks, we can make it in a stepwise manner more and more difficult. So this is some kind of structure that can help. Or we can also have what is called hierarchical reinforcement learning, where we would have multiple neural networks, where one neural network is just there to learn a specific task, and we would have like one high-level controller that delegates these kind of low-level controllers. And for sim-to-real, we already briefly discussed about domain randomization. There are other approaches, so you can strive for better simulation models of the robots. So there are lots of data-driven ways to optimize these. And there are also ways to make the adaptation between the simulated world and the real world more easy to understand for the robots. This is called under the umbrella of domain adaptation. So in total, you see we have a big toolbox, so to say, of integrating knowledge to make reinforcement learning more efficient. And this is what we can basically sum up after a study. So when we look at this toolbox that we have with all these different options, basically the more the better, you can summarize. So if you think about your problem and integrate some knowledge there, if you optimize basically these degrees of freedom that we just have, then in the end you will certainly end up with more stable, more robust, and more efficient robot models. So far about what is called guided reinforcement learning. So integrating knowledge into these learning systems. Let's get a bit more practical with a case study on locomotion. So some of you may be aware of this robot. So this has been developed basically down the street here at the Fraunhofer Institute for Material Flow and Logistics. So this is a two-wheeled robot, kind of balancing on these two wheels, having these two grippers, kind of a simplified robot kinematics for transportation tasks, if you want. So here you see some applications that it can do. So it can carry boxes and objects of very different shapes and move them in a dynamic way. And this is kind of one robot that we used as experimentation platform for these learning-based control mechanisms. And I want to guide you like a little bit through the design decisions that we made there. And in particular, we selected a couple of these methods that we just saw from the toolbox. And the first thing that we want to make sure, so we already heard that simulation plays a very big role in training these robots. So the first thing that you want to do is you want to have a good robot model. And this is what kind of it looks like. So it basically starts always from CID data of the robots that you have, and then you have different data-driven ways to improve the model. So for instance, you can look at how the actual motors of the robots behave. You can create a model for it. You can look at the sensor signals, how they look like on the real robot. You can integrate it into the simulation. And this way, step by step, reducing the gap between simulation and reality, giving the robot and the policy that you train in simulation a greater chance to transfer actually then also to the real physical robot. And domain randomization, of course, plays a role as well here in this case. So for instance, you can train the robot in different variants. So for instance, one where it carries objects, one where it does not carry objects, one where the arms are lifting, one where it's just in this balancing mode. And this way the robot learns to cope with very different task variants in simulation already when you train the RL agent. And talking about the RL problem definition, so as we heard, there are like these three big dimensions that you have in kind of design decisions. So let's talk about observations and maybe look at this maybe from the design perspective. So what makes sense for this robot to perceive if it wants to learn to locomote? Any guesses on your end? So which kind of sensor signals would we want to connect to the neural network? Any guesses?
Kind of objects are in the environment, for example, boxes.
Yep. So from a computer vision module, for instance, we could give the positions of the desired objects, of course. What else do we need?
Gyroscope.
Gyroscope, very good. So the internal data and perceivements of acceleration, which could give us like velocity signals also if we integrate it. Another idea?
I don't know how the sensor is called, but you can have the balance of an item, like if it's balanced.
Yeah, this is something you would typically integrate from the gyroscope. You could also take the motor encoders, so where kind of what the wheel positions would look like. You could get the wheel velocity in this case, which may be interesting for balancing. So you see, even for this very simple robot and this very simple task, there's some degrees of freedom for the observation level. And trust me, it makes a big difference what the robot perceives when you want to train this task. How about the rewards? So if we are looking at if we want to train a locomotion policy, so a policy that moves the robot, what should we integrate? Which terms would make sense?
Well, whether the robot successfully moved an object from point A to point B, that would be something that should be rewarded, I'd say.
Yep. This would be similar to what we saw in the manipulation example, where like the robot pushes an object from position A to position B. This could be, of course, one thing. Other ideas?
Staying in balance, not falling off.
Right, exactly. So this is kind of staying in balance can be a success. So and this is something you would typically also formulate as a task reward. So not falling down. So a pre-assumption before you can do anything interesting with this robot, of course. And thinking somewhere in the middle, if we're talking about locomotion, you would typically for instance, if you're familiar with the robot operating system and this planning approaches, you could also couple it with a velocity vector. So given like a linear velocity and an angular velocity that the robot should follow. This would be somewhere in between on the semantic level. And lastly, if we defined the observations and rewards, it's about deciding which actions the robot should take. So what could this be for this kind of robot? Yep.
Move and rotate.
Move and rotate. This would be what I would guess is integrated into the rewards. So this would be integrated as commands. For instance, if you have this velocity following function, this would be integrated as commands into the rewards. The actions in this case, they would be more on the motor level itself. So because you give like the velocity command as input, and you want the robot to follow it and to keep balance. So this means with the actions, we need to have the neural network communicating with the motors itself. And this could be, for instance, that we send a wheel velocity to the actuator or a position or whatever. So, and this is kind of a great example of how end-to-end reinforcement learning for robotics applications looks like, because you as a user, you provide, pick me this package or move with this velocity, and the robot, without being programmed for it, learns to control the motors on its own. Of course, jump in.
Why did they decide for 2 wheels and not for 3? Because then you have this gyroscope, a little less stress.
Yep. So very interesting question about design decisions of the robot. So we could probably discuss for half an hour. So this is mostly about reducing the footprint of the robot when you have like very narrow passages, and about also if you like think about scaling up, storing the kind of dozens of these robots, then you would be with a very small footprint in this case. Thanks for the question. And so what can we actually do with this setup? So we can train lots of tasks, and this is where it becomes really fun. So on the top, we see different variants of locomotion policies, so neural networks that control end-to-end this robot. And on the bottom, we also see one of the strengths of this whole paradigm of reinforcement learning, because if you train for the task that we see in the top row, we can also generalize based on the power of AI to tasks that you have not been trained for. So for instance, you can deploy the robots in different environments, as we see in the bottom middle, or also with unknown objects, as we see on the right, which in this generalization power is really one of the big advances that we have with robot learning, in particular with reinforcement learning for robotics. And yeah, so this kind of also goes, and I mean, the title is Dynamic Robot Control, of course, so we really push this to the limits. So we want the robots to not just learn somehow to balance, but we want it to behave and to act in a very agile way. And this is what we have also seen in the recent examples. It's true for this as well. So we can really move in a very agile manner with this robots trained end-to-end. This is what we see here with some very quick alternating commands for linear and angular velocities. And we see that the motors, which are kind of directly called by the actions of the neural network, they really operate at the physical limits, meaning that it's going as fast as this particular robot could be, and this is just explored from this paradigm of reinforcement learning and AI. Okay, then let's spend a couple of minutes for the choice of action space. So for the robot that we have just seen, this is already kind of an interesting choice as it turns out. And typically in reinforcement learning, how it works is you have your policy, and this operates based on the given observations and provides an action. And on the physical robot, it would be then transferred via a low-level controller to the torques that then actually drive the motors. And there's one idea, one very recent idea, to combine these two things into something that is called a generalized action space. And this offers like new options to automatically switch between different action spaces, as for instance, for the robot that we've just seen, if we would move, for instance, with a velocity control, we could also switch to a position or torque control just with this kind of overarching action space design. And yeah, this is a bit of theory. I will skip it for now, but the point is that you can basically have a lot of action spaces expressed in this generalized form. And then you can start really to compare for a given robot which action space performs best and makes most sense from the design decisions. So which action space gives the best efficiency and performance for a given task. And yeah, so what does this mean? So we have analyzed this, and this from a very recent research project between Lamar and the MIT Institute. So this is where we looked at how, for very different robots, the choice of action space plays out. And I just want to give like one example and compare the choice of action space for the two-wheeled robot that we have seen and a quadruped robot. And what we see from these tables, we don't need to go in the details, but we see very different action spaces from top to down. And green means it's performing very good, and red and orange means it's performing not that good. And what we see is that for the two-wheeled robot, action spaces like torque control, velocity control, so everything that has a high dynamic, they work pretty well and produce great results. While if we go to the top of the table, position control does not seem to be the right choice. And if we then look on the quadruped robot on the side, we see almost opposite trends where the position controlled action spaces perform very good, in particular with like high stiffness and damping values, while torque control, so the last row of the table on the bottom, performs very bad. So this is, I think, a great example of how design decisions in reinforcement learning generally can be estimated, because you really need, although it's simplifying the process of generating controllers, you still have a lot of design decisions, and there's probably one key takeaway that we can have. And if you have different robots, you of course need to think about which knowledge you want to integrate and how kind of you formulate mathematically the problem that is then solved and integrated into the neural networks. And I would say, in the interest of time, I closed the second lecture almost at the minute. And if you want to know anything about these works, just feel free to reach out. Check out the works that you see there on the right, or just stay here for a couple of questions. I will be here for 5 more minutes roughly.